Hi, everybody. Welcome back to AP Physics C. This is topic 8.4, electrostatic equilibrium. This is going to be a very important little topic because of the graphs that you can kind of see already on this page. So these are going to be two very important graphs that you need to kind of remember what they look like. Okay. So what happens is many problems in the FRQ section are going to involve conductors and or insulators. And the properties of those two are going to be different because they're different materials. So remember, a conductor is an object or type of material that allows the flow of charge, right? Where the flow of charge is what we call electric current in one or more directions. The way you can think about it, metals are great conductors. And then an insulator is a material in which electric current does not flow freely. And you can think about these are nonmetals. A lot of times the way it works out is the conductor will be like a metal and then insulator will be something like styrofoam. And they're going to have their own properties. And there's one thing that we're going to focus on. This is going to be the focus of this particular video. Sorry. All right, so the main focus of this video is this electrostatic equilibrium. So this is going to occur when there is no net motion of charge in an insulator or conductor. So yes, you see the word static, right? Or, and static meaning not moving, but the objects are going, or the charges are going to shift, right? So it's not a flow, right? But it's going to be a shifting of the charge so that they can start behaving in this electrostatic equilibrium manner. So when an insulator is in equilibrium, the excess charge of an insulator is distributed throughout the interior of the insulator as well as the surface. So what does that mean? That means if I have an insulating material, everything's going to be, and we say it's a positively charged insulator, all that charge is going to be spread everywhere, okay? So it's going to be spread throughout, thus creating an electric field inside and on and outside the surface. So this first graph is what it would look like for an insulator, right? So this right here and here, right, is the surface of the material. Okay, so leading up to the surface, the electric field inside of an insulator is going to be a linear graph. And then, we'll talk more about this later when we put more numbers to it and more expressions to it. And then once you get outside, then you get this inverse relationship. And we'll talk about where that inverse, that E equals KQ over R squared comes from here in a minute. All right. Now, when in equilibrium, the excess charge on a conductor lies on the surface of a conductor, making the electric field inside equal to zero. And something to remember is that the electric field is perpendicular to the surface of a conductor. So if I have a conductor and it is in equilibrium, I have no charge inside and all my charge lies on the outside, right, of the surface. And so the graph on the bottom, right, is a conductor. And then right there is the, how we graph that. Now, just very quickly, where does this E equals KQ over R squared come from? So remember, we had in topic 8.2, we had the equation that was Coulomb's force, right? And then in the last video, we had, F equals QE. Well, one of these Q's, right, cancels this Q, and then you get that relationship that you see there, right, of E equals KQ over R squared. Okay, so something to note, even though these are one's an insulator, one's a conductor, once you get outside of the surface, it still has that same KQ over R squared manner. Okay, So now let's look at an example with electrostatic equilibrium. So we have a particle of charge 2.0 times 10 to the negative 8th coulombs experiences an upward force of magnitude 4.0 times 10 to the negative 6 when placed in a particular point in an electric field. Part A, what is the electric field at that point? And then B, if a charge of Q equals negative 1.0 times 10 to the negative 8th coulombs is placed there, what is the force on it? Okay, so the first thing we need to do is figure out what is the E field, right, at that point. So easy enough, we use our 8.3 equation, E equals Fe over Q. And so we're going to do the amount of forces it experiences, 4.0 times 10 to the negative 6 newtons, divided by its charge, 2.0 times 10 to the negative 8th coulombs. And then we're going to get the, then we find that there's going to be 200 newtons per coulomb at that point. Okay. And then, and if you want to keep going, what is the direction? Because this is a positive force or an upward force, the E field would be up at that point. So draw a little arrow for up. And now for part B, if a charge of negative 1.0 times 10 to the negative 8 is placed there, what is the force on it? Well, we just, do the algebra, get this equation that F equals QE. And then we just, kind of went backwards. So we do 1.0 times 10 to the negative 8th coulombs. Times 200 newtons per coulomb. And so we would get an answer of, or a force of 2.0 times 10 to the negative 6 newtons. Now, this one would have a downward force because we know the E field at that point is up, but because this is a negative charge, it goes opposite. Okay. Now, just quickly, if we want to use the equation that we just kind of derived on the last slide, let's say we want to add in the question of like how far away are these 2 points or are these charges located? So what you would do is manipulate this equation, right? And you would end up with the square root of KQ over E. So note that, yes, it has to do with the charge, but again, that E, right, is kind of, is the proportionality, right? So I get square root of K, so it's 9 times 10 to the 9th times Q, 2.0 times 10 to the 8th, negative 8th, divided by 200. And so we find that the distance that these charges would be 0.948 meters. Again, this is not one of the questions. This would just say like, how far is the test charge away from the central charge? Okay. All right, so in the next video, we're going to keep working on these electric fields, but what we're going to do is we're going to look at specific distributions, which is a very common FRQ question.